I'd like to talk about the basics of the refrigeration cycle before we get into the nitty-gritty computational details that can be kind of complex about analyzing the four components of the refrigeration cycle. So let's get started looking at the four basic components of the refrigeration cycle. So there's a reason I'm doing this, and I'm just going to try to give you a high-level view of the four main components of how a refrigeration cycle works, because I had a hard time absorbing it myself. Now, I've made it through, and as a practicing engineer, I've done a good bit of work on refrigeration cycles, analyzing refrigeration cycles, implementing them, and certainly using them to our advantage in manufacturing. This slide and basically this video is dedicated to my dad. So here is a picture of our last family photo together. And I reminisce about asking my dad as I was growing up, I'd say particularly in high school, asking him, how does a refrigerator work? By golly, he would dutifully recount the way a refrigerator works. He would talk about the four basic components of a refrigerator, and I would dutifully, respectfully listen. And I didn't absorb it. And I'll swear that I couldn't exactly remember the four basic components, didn't have a feel for how these things worked, but by golly, my dad was so patient and he explained the refrigeration cycle to me over and over and over again. And it wasn't until I got into college and started taking a course in thermodynamics that finally I gained the ability to understand these components, to remember what these components are, and also be able to analyze them numerically. So let's go over the four basic components that I can now recite by heart, but wasn't able to do so in high school. So let's start with the compressor. The compressor part of a refrigeration cycle is the part that requires the electric power, and it's the thing that you hear humming. If you listen to your refrigerator, you can hear it humming and humming, and that's the compressor motor rotating and driving the compressor. Okay, so compressor is an important part. All four of these are important. So this compressor takes the refrigerant and increases the pressure of the refrigerant, and it turns out to be a superheated vapor, in which and that superheated vapor refrigerant goes into a condenser. Now this is where the heat is transferred out of the refrigerant into the surroundings at TH. So this is the part, if you turn your refrigerator around and the coils on the back of the refrigerator, you can feel, ooh, they're hot, they're hot. That's the condenser part of the refrigerator. Now, it gets a little more complex. And so that condenser does condense the refrigerant down to a liquid. It's a high pressure liquid. And then it goes through this expansion valve. And that's something that I had a rough time understanding what that was all about. My dad would explain it and I wouldn't get it. But anyway, here's an expansion valve, and it's nothing more than a little throttling valve. It's just a tiny, it's a valve with a tiny little orifice opening, and the pressure drops. So we go from high pressure liquid, and it turns out that when the pressure drops of this refrigerant, the refrigerant gets very, very cold. Pressure drops down to a certain pressure, very cold refrigerant, and that's where we get our bang for the buck. That's where this refrigerant goes into the evaporator section. It's a heat exchanger is all it is, and it's absorbing heat from the cold space up in the freezer section of your refrigerator. Cold space. An evaporator is nothing more than a heat exchanger. And in high school, I had a hard time understanding what a heat exchanger was, but I got a better feel for it the more experience I got. And that brings us to and those are our four components. So out of the evaporator, heat is absorbed, and it turns out that it's absorbed and at constant pressure. And then we go right back into the inlet of the compressor as saturated vapor, refrigerant, and then we go back around for another cycle. So you see that these four components, and let me say them out loud again. So I hope you can remember them. The compressor is a steady state, steady flow open system. The condenser, it's a steady state, steady flow, one inlet, one outlet heat exchanger. The expansion valve, it's nothing more than a valve with a tiny little orifice opening that drops the pressure from high pressure to low pressure. Finally, the evaporator, steady state, steady flow, open system control volume. There it is. It's just a heat exchanger operating at constant pressure. So it's my suggestion that you try to, you study your textbook for a little more background. This is section 10.2 in your textbook. Try to commit to memory, not necessarily all those words I gave you, but just those four words, the four components: compressor, condenser, expansion valve, and evaporator. Those are the four components. There are four only components of a vapor compression refrigeration cycle. Why do we call it vapor compression refrigeration cycle? Well, refrigeration, we're transferring heat from cold to hot. Got it. Why do we call it vapor compression? Because this refrigerant that we're using, it's a phase change substance, and in part of the cycle, it is a vapor. In other part of the cycle, it's a liquid. So it's changing phase. The refrigerant is changing phase as it's going through this cycle. So over here, we've got vapor. Over here, we've got liquid. Down here, evaporator, we've got a saturated mixture. So that's why we call it a vapor compression refrigeration cycle. The compression part, it's because we have a compressor. We go from a lower pressure up to a pretty high pressure. Now let's see, all of these things. Let's plan for what we're going to analyze before we get into the nitty-gritty details. Always, always, when you have an engineering problem associated with a heat pump or refrigerator, always draw this schematic sketch. It helps remind you that you're transferring heat from a low temperature to a high temperature. Seems kind of strange, at the expense of needing power to drive. So that's a key. Start with a sketch. The other thing is asking, well, what is a substance? What's the working fluid within this black box? Is it refrigerant R134A? That'll be most of your homework problems. Will it be refrigerant R22? Maybe one or two homework problems. Will it be ammonia, NH3? Maybe one or two homework problems there. But by far and away, refrigerant 134A will be the working fluid that you'll be using. Let's see, another thing. Oh, once we've drawn the sketch, remember the dots? We've got these dots over top of Q.L, Q.H, W.net. Think of a refrigerator. It's not just sitting there and the heat transfer is in kilojoules, is it? It's kilojoules per second. The refrigerator is operating at a steady rate when it's running. It's operating steadily when it's running. Okay, so that's Q dot, W dot. It's all about the dots. And remember our four components: our compressor, our condenser, our expansion valve, and our evaporator. Each one of those is a steady state, steady flow, open system, and each of those has one inlet and one outlet. And so you're pretty good now at analyzing steady state, steady flow, open systems, one inlet and one outlet. You're pretty good at that already. So you're going to ask yourself, and when you're solving these problems, what is the energy sought? Well, it's either going to be the refrigeration effect, Q.L, or if it's a heat pump, the energy sought is Q.H, one or the other of those. What's the energy that costs? It's always the power required to drive the compressor. That's what the energy that costs. So you can get the coefficient of performance, whether you have a refrigerator or a heat pump, right off the top of your head. You don't need a formula sheet for this. Now, let's look ahead a little bit. Let's see how the temperature entropy diagram fits with the components. Okay, I hope that I've convinced you that we've got 4 components for a refrigeration cycle. Let's start with the compressor. Here's our compressor. What's that going to look like on a temperature entropy diagram? The inlet of the compressor is going to be a saturated vapor. Oh, I'm drawing a picture of the ideal refrigeration cycle where this compressor is fully insulated. We're always going to have a fully insulated compressor, but we're going to say that the compressor is also reversible and adiabatic. That's why I've got this vertical line here going from saturated vapor up to superheated vapor isentropically, constant entropy compressor. Then we've got this heat exchanger operating at a constant pressure, no pressure drop from P2 to P3. It's one inlet, one outlet. All we're doing is removing heat. We're not doing any work. We're not lifting a weight in the condenser. So here's our process 2 to 3. Constant pressure condensing. So we're condensing the superheated vapor down to a saturated vapor and then all the way across the dome to a saturated liquid. So saturated liquid is going into the expansion valve for the ideal cycle. There may be some little tweaks, but we want you to get good at this ideal cycle first. Okay, we've got saturated liquid going into the expansion valve. A valve. Valve's not lifting a weight. There's no rotating shaft coming out of a valve. It's just dropping the pressure from 3 to 4. Wow. Well, that's very irreversible, isn't it? When you drop the pressure of an open system, when the open system is dropping the pressure of a fluid, refrigerant, and we're not getting any work out, that's very irreversible. Look at that. So 3 to 4 is shown as a dashed line. Very irreversible process. 3 to 4, very irreversible, but very cold. So coming out at T4, you're at a lower pressure, but look at how the temperature has gotten really cold. That's what you want out of your working fluid, refrigerant. So that way you can absorb heat from the cold space into your evaporator, process 4 to 1. So we're starting at a saturated mixture. We're adding heat to that. We're not lifting a weight, no shaft coming out, but at constant pressure up to, and we're adding energy, adding energy until we reach a saturated vapor phase. Look, it's still kind of cold. It's still cold. Look, it's constant temperature. It's still cold, but now it's going in the compressor to repeat the cycle. So it is my hope that this sketch, you can study on it, you can pause, but it's my hope that you spend a little time hooking up the temperature entropy diagram look for the ideal refrigeration cycle. So you see on the slide, I've called it the ideal cycle, and it's ideal because the compressor is reversible and adiabatic. We're going to correct for that a little later in the chapter, but for right now, let's focus on the ideal. Reversible adiabatic compressor, okay, the condenser, constant pressure, not lifting a weight. Expansion valve. Well, it's very irreversible. So even in the ideal cycle, we have some built-in cycle irreversibilities that we can't do anything about. And then finally, the evaporator, constant pressure evaporation. So spend some time. I'm vamping a little bit to give you some time to maybe eyeball the 4 components and try to see how the 4 components are associated with the ideal TS diagram, temperature entropy diagram, that we're going to be using throughout Chapter 10. Hope that helps. If you're eager to start crunching numbers, I've got a fully worked out example problem that I selected out of chapter 10. It's problem 10.4, and you can go to my homework solutions playlist and click on problem 10.4 if you're very eager to start seeing, well, how does all these generalities fit into a real honest to goodness homework problem that's just about a real world problem. So if you wish to go right now to a fully worked out problem, start to finish, go to homework solutions playlist, problem 10.4. Okay, so what's the takeaway from this video? Well, the vapor compression refrigeration cycle, what enables us to do is transfer heat from cold to hot, but at the expense of investing work or power to accomplish the objective. You might keep in the back of your mind that I'm openly admitting that at the high school level, early undergraduate level, man, I couldn't even recite the four basic components of the refrigeration cycle. But by golly, I can do it now. We've got a compressor, we've got a condenser, followed by the expansion valve, then the evaporator. By golly, I still dedicate this video to my dad, who was so patient with me, explaining to me over and over again how the refrigerator worked. I wasn't absorbing it, but he was just always happy to share with me how refrigeration works over and over again. And as if, and he didn't yell at me for being dumb or not absorbing it. It was just what a gift that was. All right, well, in the next videos, I'm going to go through the nitty gritty for each of those four components and how will you analyze each component as you're running through the analysis of a refrigeration cycle or a heat pump cycle.